It works.
Yeah.
Is it quarto?
There we go. Right. Okay. So the talk this week is on Logistic Regression, chapter 13. It may not be the best chapter. It's quite like the stuff that we've had before. It's just another step along the road. Basically, we've had like linear regression with a normal distribution, and then we've had regression with alternative distributions, and now we've got logistic regression that can be used for classification, but it's basically the same stuff. Okay, but how is it different? So instead of the response variable being quantitative, i.e., for instance, 3,540 people are going to hire a bike from the bike scheme, as we might have had in the previous week, the response variable now has to be categorical, i.e., is the person a voter or non-voter? Will this person make a claim against their car insurance or not? Or or as we will find out later, will it rain tomorrow or not? So these are all examples of a binary categorical response variable. So it's slightly outside the topic of this week, but it can be extended further. So the logistic regression that we're looking at now just has two options, but there's something called multi-nominal logistic regression. So you can have more than two if you wanted to. Okay, and then it goes on. There's a section in 13.1 about odds and probability. And we'll see a little bit later as to why they put this section in. But if any of you are gamblers, this could be quite useful. It basically gives you the formulas so you can convert odds to probability and probability to odds. So if you want to be a bookmaker or gamble without giving the bookmaker too many holidays with your money, yeah, those would be quite useful. So when we go into this, this is like a really good graphic on there, because the logistic regression, I think it basically works on log odds. But when we look at the numbers of log odds, they don't actually mean anything to a normal person, basically. So what we would be more interested in trying to assess something is either the odds of something happening or the probability of something happening. So I think deep down in the mathematics of it, it's still a linear model, basically. So it does use the log odds as on the left there. But what we are seeing are non-linear functions, basically. So which is the ones in the center and the right there, basically. Right. Okay, so the theme of this chapter is to build a logistic regression to predict if it's going to rain tomorrow. The model is started by predicting YI by using today's 9 AM, I can't spell humidity by the looks of it, humidity level XI. What would be the most appropriate model structure? Should we be using Bernoulli, gamma, or beta?
It's a question.
Take a guess. Take a guess.
Okay, I'm blindly gonna go with beta.
Oh, close.
Which is
close,
basically
but
a gamma version, a particular case of the gamma one, no?
no.
Oh,
Bernoulli.
Yeah, it's basically the reason for that.
oh, is a 0 or 1? Okay.
Is because the response variable is a discrete variable. It can only take on two. Yeah. So it's either going to be one thing or not that thing. It's either going to rain or not rain.
Okay.
And I think when I was learning probability, I think the Bernoulli is using that because basically it's either heads or.
Yeah, I thought like it was a probability. That's why I said beta or gamma.
So if I got it right, then a beta can take any value between 0 and 1, and it's continuous, right?
Yeah.
But the Bernoulli is like either 0 or 1. So
Yeah.
it's a binary outcome. That means, would it be correct to say that it's Bernoulli then, or?
Yeah, it is Bernoulli.
Yeah,
No, I mean that's what we want in a logistic regression, because it's a method of classifying things between two different. So it's either going to rain or it's not going to rain. So It's either going to be one or the other.
Then what
it's
about the
not
gamma?
continuous.
What about the gamma? What the gamma does?
It didn't give me much information of that in the book, so I don't know. That was just,
I think it's a special case of the beta.
yeah, that was just a random one to confuse you.
Yeah,
I'm cheating
it's a
and looking through.
transformation.
Yeah.
So I was cheating a bit and looking at Wikipedia, and I didn't. But at just at a glance, it says a continuous distribution.
Okay.
So I guess like binary outcome means discrete, right?
Yeah, it's discrete rather than continuous. So yeah, this is some of the code from there. You will recognize the code. Indeed, it says stand GLM there. It's still part of the general linear model. The main difference you may notice in there is that where it says family, it says binomial. But really, it's like we've had in previous weeks. I mean, it's virtually got the same code in it. Okay. So, however, whereas our prior understanding left us open the possibility that the probability of rain might be near 100% as humidity levels max out, I think this is based on the graph from the previous code. But what we see in the data is that the chance of rain is at the highest humidity levels barely breaks 50%. So you can have 99% humidity levels, and the chance of rain is higher than lower levels of humidity, but it's still, it's 50-50 really. So that can just be updated there. It's a relatively simple code to write.
So basically, we update with prior false, with the prior false. Huh?
Yeah. So the information that was coming out of the prior was possibly suggesting that if you had a humidity level near 100%, you would have a very high probability of rain the next day. In reality, from the data, that isn't the case. So it's still the higher the humidity, the more it rains. It doesn't rain very much. And then basically it says to check the trace density and autocorrelation plots. We've all seen the fuzzy moustache before. The density overlay. And the ACF.
No,
they all look
we
just
don't
the same.
hear you well.
Yeah, they all look just the same as they do previously.
Mine is bad.
I don't hear you.
Hello?
Stay
Yeah,
out.
your mic is bad.
Oh.
Okay.
I don't know. Should I talk a bit louder? Is that going to help?
Yeah.
Better.
Yeah.
No,
Right.
it's better. It was
Okay.
just like the poor misconnection.
Yeah. Okay. Right. Let's go on to the next bit. Yeah. So this is the data. Basically, there's a lot more times in Perth where it doesn't rain. So that's the bottom one there. The days where it rains are the top half here. Now it's got the humidity along the bottom. There's not much rain where it's a low humidity, but it's basically a higher number of days where it doesn't rain. So there aren't many rainy days in Perth. So if you like your sunshine, go to Australia. Right. And this is also this is the rain rate by humidity bracket. So between 0 and 50, it's all pretty low. And then after the humidity goes over 50, there's a steady progression up. But as you can see, when it gets to the top bracket, 90 to 100%, the probability of rain the next day is still 50-50 roughly. So even if it's incredibly humid, you're not guaranteed rain. Right. Okay, so suppose you're in Perth today and you experience 99% humidity at 9 a.m. To predict whether it will rain tomorrow, we can approximate the posterior predictive model for the binary outcomes of y, whether or not it rains. So this is basically taking the 99% humidity example, putting it through some code and making a prediction on there.
So we have to go like to the log odds, calculate the odd, then draw a random sample inside of it, basically. Okay.
Yeah.
No, first odds, then log odds, then probability, then random on the probability. Okay.
So for every 1% increase, so this is posterior summaries on the odds scale. So for every 1 percentage point increase in today's 9 a.m. humidity, there's an 80% posterior chance that the log odds of rain increases by somewhere between 0.4 and 0.5. More meaningfully, for every 1% percentage point increase in the humidity at 9 a.m., the odds increase by somewhere between 4.2 and 5.6%. So yeah, it's always good to convert them because basically log odds don't really mean anything to anyone. Right. And then these are the results overall, and I think it's about 54% or something like that chance of rain. That's what it came out with, I think. Okay, this is actually the more interesting bit than the logistic regression. It's actually the model evaluation on it. So like, how fair is the model? How wrong is the model? How accurate are the model's posterior classifications? So we've seen the general format before. There is some cross-validated stuff in there, and ELPD, which I have glossed over because it's kind of the same as previous weeks, but there is some interesting stuff in here. Oh yeah, and again, there's the posterior predictive check. That all looks perfectly normal on there. So yeah, when you look at the classifications there, you notice that our classification rule, in conjunction with our Bayesian model, correctly classified of the 1,000 total test cases, 817 of them. Thus, the overall classification accuracy is 81.7%. But there's a difference between the sorts of classifications that it does on there. So at face value,
is it okay if we go back one slide? And maybe you're mentioning this here, but I mean, if we look at the baseline, if you have a model that always says that it won't rain, you will have 80.3% accuracy, right? Or was this or am I confused?
Don't worry, if we go on to the next one, it will explain it.
Okay.
But there's a difference between what this model is really good at is predicting when it won't rain. It's pretty poor at predicting when it will rain. But yeah, that's on the next page basically. So at face value, it seems pretty good, but you look closer, our model is much better at anticipating when it won't rain than when it will. Among the 814 days on which it doesn't rain, it correctly classifies 803 of them. So that's a classification rate of 98.65%. So that's really good. This is referred to as the true negative rate, or the specificity of our Bayesian model. In stark contrast, among the 186 days on which it does rain, we correctly classify only 14 of them. So 186 days of rain, and the model only predicts 14 days correctly. So that's not very good. this figure is referred to as the true positive rate or sensitivity of our Bayesian model. And yeah,
yeah, I think Eric was right. So we say, if we say it won't rain, if we basically classify everything, it won't rain. In Perth, it won't rain.
Yeah, I think it's about, you know, one time out of 100, you think it won't rain, you'll need an umbrella. But it's the predictions that it makes for when it rains that are really bad on here. So basically, you can use a function on there called the classification summary, which is in the Bayes rules package. And so that gives the confusion matrix, which has the results on there. So that has the 803 times where it didn't rain, and the model said it won't rain, and the 11 times that it got wrong. It also has the predictions where it did, where the model said it would rain, and it's got that wrong 172 times and only got it right 14 times. So then it gives the accuracy rates. So the sensitivity, this is where it's picking up whether it's going to rain or not, because it predicted that it would rain. It was only accurate 7.5% of the time. And the specificity is, yeah, the 98.6 on there. So it's really good at predicting when it won't rain, and it then basically adds them together to give the overall accuracy on there. But it's good to look at those two different measures on there, because that can affect how useful your model is. And you can actually vary that as well, which I think we come on to in a little bit. Right, okay, so yeah, it's basically the trade-offs in sensitivity and specificity. As analysts, we must utilize context to determine an appropriate classification rule with the corresponding cutoff. In doing so, there are some trade-offs to consider. As we lower the cutoff, sensitivity increases, but specificity decreases. As we increase the cutoff, specificity increases, but sensitivity decreases. So if we go back a slide, in the code there, the cutoff is 0.5. So that basically means if the probability it's going to rain is 51%, it's going to be classified as a rainy day. And what they probably should do with this one, because it's really good at picking up when it won't rain, but it's not very good at picking up when it will rain, is lower that cutoff to make it a bit more sensitive, basically, which I think they do, and they have another rain model 2 on there. So I think that's in the text. Okay. There we go. Yeah, so basically, what we've learned today, logistic regression is quite like the other forms of regression. It's just a response variable that has a significance difference. It's a classification method, but the maths behind it is pretty similar. The best bit is the model evaluation, where we learn about the true positive rate or sensitivity, and the true negative rate, the specificity on there. So that's probably, if you're wanting to learn to statistical model stuff, that's probably the most useful thing coming out of that chapter.
Okay.
Yes, Brendan says this is a really interesting problem that the data science community calls imbalanced learning. There's more information. There's a link to more information.
Ooh. Yeah, I'll read that.
Yeah, I don't. I'm just checking, but we have prior, you know, in this model probably. So
Yeah,
can the prior a bit correct also? That's all that the. I'm trying to.
Yeah, there was a prior in there.
In the model. What was our choice of prior?
But can we? Oh, okay. Yeah, that's
Here, prior intercept. How do they justify this prior?
So we use the stand GLM, and then the rain tomorrow based on humidity AM, as we know, and there's like.
Yeah, they say there is roughly 20% of chance of rain. That's why they use like the -1.4 with the center beta intercept, which is like 1.4 prior intercept. But yeah.
Yeah, I think that was probably based on the log odds. Because
yeah,
if you go,
right.
if you go back further, on here, the log odds, they go down into minus figures, but the probability can't go into minus figures, and the odds can't either. You can't have minus probabilities, always between 0 and 1.
Yeah, and checking like their prior check, the random model, the 100 prior data set, like the generate with the prior. This doesn't seem too bad. I don't know. I think like maybe there is some tuning here, but that can help a bit, like this, because like if you said there's 20% chance of rain per day, and if you check the data, you have less than 20%, no? Well less. So I don't. So yes, I don't know. This is, well, we cannot solve this issue, but
we use the logistic regression to say it rains or it doesn't rain. So one is 0 and one is, and the other is 1. So we have a binary response variable, and then we use just humidity and the stand GLM model. Then when we check for the result of this model, we use the confusion matrix and the accuracy rate. And we do this with this classification summary function within the model. And then I set the cutoff at 50%. Is that something that is fixed like that? How I can change it? I can't hear you. I don't hear you. Okay.
it's good. Yeah, I don't know. You can correct that. I will check. We have to check the article, like send in the chat. But yeah.
Will, I don't hear you. I don't hear you. Can you hear Will, Oliver?
No.
No, we don't hear you.
Sorry, Will.
No, well, we don't.
Basically, you can change the cutoff figure to make the model more or less sensitive. Okay. Yeah. Okay, more or less sensitive. Okay, so with 50% is like balanced result.
Yes. So with the cutoff, like on 50%, if we lower it, we will have more we'll have more days that are classified as rain with no rain, and we'll have more days classified as rain with rain. That's what we'll get, I think.
So let's see if I get this right. Logistic regression, we're sort of generating a probability, or we're generating something on the 0 to 1 scale. And then does the cutoff mean that the normal cutoff is in the middle at 50% probability, and we can change it to 0.6? So everything that is 0.6 below is classified as false, and everything above 0.6 is true. Is that how the cutoff works? Okay, nice. I'm wondering if Zoom just played a trick on you, Will. Sometimes it somehow configures a different microphone for me. So that somehow,
Yeah.
I don't know, some weird microphone. So at least for me,
I think
sometimes
so.
it works going to settings and verifying that the right microphone
Yeah.
is in there.
Then you can go to your microphone on the left side of the screen, on the bottom left. There is the and then there is select microphone. Maybe use just ask same assistant. No, we don't hear you. I don't know what's happened. Maybe you can put like the headphones. Have you got any headphones or something like that? Because sometimes it's an error. I've got the same issue with my computer. So if I don't use the headphones, the sound is very little, like something gets stuck inside, because I use the Bluetooth headphones once, sometimes. So I don't know.
Oh.
Nothing. No. Now you're muted. You're muted.
Yeah, you're muted.
I think I'm suspecting that Will has a secret plan to create this Bayesian lip sync algorithm, like lip read algorithm, and this is just a step in the propaganda.
But you are
Yeah,
muted.
you are muted.
Will. You are muted. Now you are unmuted.
It's not me.
Very bottom left of your screen. Unmute yourself.
I mean, this is clearly a applied logistic regression, like the probability that the mic will work in the next minute. But I'm wondering what our input variables are.
The difficulty of the question, of the exercise. Anyway, I think we're good. Next week is also Will, I see. No. Let me check next week. Yeah. So next week also Will. So question is, does someone want to do the week after?
I could do a week after.
Cool. So I add you to the list, to the hierarchical model. Oh, that's cool. Cool topic. Erika. This is G, no G here. Okay. It will be, we are closing it. We are doing it. 1, 2, 5 more chapters.
Yeah, we are going to make it, of course. Yes.
Yes. So congratulations, everyone. Oh, Will is back. No. Well, anyway, so congrats to everyone. I think we can see each other next week, and I will have to buy some ingredient to bake my wonderful salad. So bye.
Bye.
See you next week. Bye.
See you next week. Bye.